Silicon carbide is stirring up the market for power electronics, specifically in the traction inverters at the heart of electric vehicles. Silicon carbide MOSFETs have faster switching speeds, higher breakdown voltages, and other high-end characteristics compared to silicon IGBTs. But they are still relatively new and experiencing some growing pains. And as a result, they tend to be more expensive than silicon when packaged into power modules. Infineon is trying to minimize the drawbacks of both technologies. It recently released what it calls the first fusion power module that combines silicon carbide MOSFETs with silicon IGBTs all in a single module. So I think it makes sense to maybe start with silicon carbide, which is becoming a bigger and bigger topic as it relates to the electric vehicles and specifically the traction inverters. So I'm just wondering if you can start out by going into why this transition is happening and sort of some of the technical differences compared to silicon.
So thanks for asking this question, and I would like to start with giving you some numbers on here. So in 2013, if you look on the BEV, the battery electrical vehicle, the bill of material most likely will range about like $2,000 per car. And that's a massive amount of, let's say, semiconductors. Also some numbers is like in 5 years from now on, is also every second car will be electrified. And also, if you have a look, also 5 years from today, the XEV market, the SiC market, in drivetrain, the power, will reach nearly 55%. So it's a dramatically increase of the SiC, and also on the same stage, so silicon, as we call it, CSE, will go down to 45%. So this is like an estimation. So the SiC market will increase, and the silicon carbide is, or the SiC is kind of a semiconductor material that has really been gaining significant attention within the electrical vehicle market, so the EV market. And as you also pointed out, particularly in the field of the power electronics, also the traction inverters. And in recent years, the SiC has been increasingly also replacing the traditional, the silicon, also in not only traction inverters, also in various EV applications. And this is also for good reasons, right? So the one of the primary drivers behind of the adoption of the SiC in EVs is the perfect, superior performance characteristic compared to the silicon of SiC. Because of SiC has, first of all, a higher thermal conductivity, so which enables SiC to operate at higher temperatures and frequencies, in making it more efficient and more reliable. And also, this is also the one of the top performance of the SiC, of the silicon carbide. It has a higher breakdown voltage, which also allows to handle higher power densities and reduce the risk of the electrical failures. So therefore, in the complete EV market, which is rising, the SiC is just being used to replace silicon in several applications in the power electronic, but it also comes with a higher price tag. So there's always like the second part of the coin, right?
So I was wondering if you could talk at all about what is driving the fact that the price tag is higher. Is it just challenges around manufacturing silicon carbide specifically, or is it just economies of scale? You know, silicon has been around for such a long time that semiconductor companies are very good at manufacturing it in very large quantities. Is it just an economics question, or is it a manufacturing issue as well?
So Infineon is really good, and this is also driving Infineon in both technologies, also in the silicon, so in the IGBTs, as we call it, and also in the silicon carbide. So we can do both. This is one of the major drivers also for us, to have the possibility and also to lever both technologies and to use also both technologies for us within the products. And as I'm coming from I'm responsible for the high voltage, the modules. So particularly also for a new product, the fusion. That's exactly why we're using those both technologies into one product, having a look into, right?
So as you noted a couple of times, Infineon recently introduced what it's calling a fusion power module that covers for some of the drawbacks of silicon and the drawbacks of silicon carbide by combining them both. So can you sort of take us inside the new module and just sort of walk us through what's inside of it?
James, absolutely. So let me share some insights. So where's that fusion coming from? Where's the motivation coming from? So basically, the EV applications, if you have a look on the WLTP drive cycle, so this is basically the applications are often driven in the light load conditions in this cycle. And we have discovered this in this light load discussion at the condition, 30% of, let's say, of a SiC chip content would be sufficient for driving this in the common operating conditions. It also means in the high load currents, which is usually supported by IGBT in the diode, it's driven not that common. So means basically, so the basic principle of that would be light load, we are using the SiC. In the full load, we're using the silicon. This is the motivation, the idea behind of using, let's say, two different technologies in one module. So it's the magic behind as we call it, the hybrid pack drive fusion is all about finding the sweet spot between the performance and then because we also talked about before the drawback on the SiC, the performance and the cost. This new module, the system suppliers, they can get almost the same efficiency as a full SiC solution, as a full silicon carbide solution. But the beauty is only with 30% SiC content and 70% silicon area. And this is basically a huge win. To be real, so a full SiC module can offer a higher efficiency, but again, it comes with a, let's say, a hefty price tag on that. And this is exactly why the hybrid pack drive fusion steps into and comes into here. So this is the, let's say, the perfect compromise on that. So the combination of a cost efficiency IGBT with SiC components, then you get the best of both worlds, right?
So can you maybe discuss some more technical details of the module? Maybe how many of each power transistor you're using and how they're arranged, and any other details you can shed some light on there.
Sure. Not quite sure it's a podcast, but we also video, and I've also brought that module with me, right? This is, as you can see, it's a hybrid pack drive module from Infineon. So the same package, and we're basically using a toolkit which is pretty much existing. So from back end, as we call it, packaging, and also from front end, there's the dice, and then really smartly putting everything together. This is, as we call it, like the fusion, merging different technologies together to one really new product. And so what makes the tick? In the end, it's the perfect switching harmonization between our front-end technology, the EDT3, and SiC generation 2. So this is optimized for the performance and efficiency. And also, it comes also with the charm of you can drive it with a single gate driver capability. So it's a breeze to integrate into designs for the OEMs and the tier ones. we are using the Infineon's latest die-attach technology with sintering and pairing those EDT3, IGBT, and SiC generation 2 technologies together. If you're asking for technical details, so it's got a short circuit robustness of currently 1.5 microseconds, and we can handle with the product, which is now coming up to the market, by planning end of 25 with up to 750 amps. So that means if you calculate that, we can future it up roughly up to 220 kilowatt, and ensuring a high reliability over the entire temperature range. So from -40 to +175 degree. It also has the possibility to integrate Hall sensors in the package, because it's a well-known package for the phase current measurement in a power module. And this is also very good for, let's say, for the cross-selling, as you can also use like our Swoboda sensors on here in Hyperpack Drive Generation 2 Fusion. You can put a single gate driver from Infineon also on here, which is also basically used for standard SiC applications. So for example, the EDI 3035 AS or the EDI 3040 AS. So this you can easily use, but also for the choice